Good morning. Last talk of the morning. I'll try and keep it short and sweet. It's good to be back at AbGradCon. Seeing a bunch of old friends, making some new friends, even some new enemies, Team Rocket. For those of you who don't know, they won trivia last night. So yeah, I'm going to be presenting some of my master's work at the University of Cincinnati. I'm transitioning now to a PhD at UCLA. So I'll talk a little bit about what I did and what I'm transitioning into and what I'd like to work on in the future. So a little vocab check for you. We're all different disciplines here: chemists, physics, biologists, geologists. So just to make sure we're all on the same page. Carbon isotopes, I like that a couple people have talked about this before, so some of this is a little bit review. But it's basically a ratio of carbon-13 to carbon-12, and that's in delta notation typically. You can do it on, perform this on organic or inorganic carbon, and biosignatures. So in this talk, it's mostly focused on evidence of past life. The Precambrian is basically any strata that are older than 541 million years ago. Organics, in the context that I'm talking about them, are mostly aromatic hydrocarbons that have been produced over billions of years. In other words, Carriage, which I'll discuss in a minute. And by metabolisms, I'm specifically talking about microbial carbon fixation pathways. So there's a lot of other microbial metabolisms, but we're going to focus explicitly on carbon here today. So when we're measuring carbon isotopes in organic matter, what you're looking at is organic matter that's been produced over billions of years in the Precambrian, mostly, and it comes from originally from biopolymers, so biomolecules that are made in microbes, and basically when they die, they get broken down through microbial degradation into monomers and eventually into, through polymerization and condensation reactions, turn into geopolymers, which is basically a very high molecular weight, insoluble in organic solvents. It makes up about 95% of organic matter. One caveat is that this goes through a whole large range of history. So it goes through diagenesis, which is basically everything that happens prior to burial. And then it gets buried deep down, and so as you go down in the strata, you're going up in temperature and pressure, eventually leading to lithification and, in some cases, metamorphism, which all of these things can have, to an extent, an effect on the carbon isotope signature. So how do we detect Carriage in Precambrian rocks? I like that someone else already went through Raman, so I don't have to explain too much. But basically, this is your Carriage shift in your Raman spectra. So when you see this pop up, you have a pretty good feeling that you're looking at organic matter that was biologically produced. So basically what Raman spectroscopy does is it allows you to measure this on the micron scale, so you can measure this actually on individual microfossils. So that's what we'll get into here in a second. And you can do it in situ in the thin section, so you know that you don't have to extract anything. You can just throw a microscope slide underneath there and zap it with a laser, and you know what you got. Also, it's been shown, Bill Schaff in 2005 wrote, and others wrote a paper that was showing that you can quantitatively express the relative thermal maturity of the Carriage. So someone else showed Raman earlier and said, oh, this isn't too geochemically mature. And that's basically what he's referring to, is comparing this along a suite. And so he uses what's called the RIP value. So we did a little bit of that work in my master's. And it's kind of counterintuitive. Low geochemical maturity is a high RIP value. And this stuff down here is really cooked, almost like graphite. So carbon isotopes, just a little bit more kind of background stuff. I said you could do it in inorganics, so carbonate or organic carbon. Here's the pretty equation for all you math people. And then what you can do is you can measure in the inorganic source and the organic source, take the difference, and that basically gives you the total metabolic fractionation for the biomass. And so that's basically what's mainly used when you are inferring microbial carbon fixation pathways in the Precambrian, is you're using this difference from the organic source to the inorganic source. The catch is that various metabolic pathways of microorganisms fractionate carbon isotopes differently and to different extents. So that's what's shown on this plot here, adapted from Manfred Shidlowski in 2001 and Zirkel et al. In 2005. So what this basically shows is average compositions for the inorganic species in the black. So you have marine carbonate, bicarbonate, atmospheric CO2, dissolved CO2, all roughly between 0 and -10. So in carbon isotope terms, that's relatively heavy. As opposed to these microbial fixation pathways, which fractionate carbon to a much greater extent. So anywhere from -10 to -35 for most cyanobacteria, photosynthetic organisms. And when you get down into methanogenesis and especially methanotrophy, so methane cycling, can really deplete carbon isotopes quite a ways. So when we look at this in the geologic record, this difference between the organic species and the inorganic species is notable all the way back 3.5 billion years. Potentially even to 3.8. So some of you might be familiar with the Ischua metasedimentary suite. So this is showing the organic carbon measured, the range of it, and this is showing carbon isotopes that have been altered by metamorphism. So the metamorphism tends to drive things towards more heavy values, and you'll notice actually that the carbonate values are depleted as well. These long bars here, what they represent are ion microprobe measurements in apatite grains, which show that the graphite in there has actually been preserved differently than it has elsewhere in the rock. So there is some suggestions that carbon isotopes and carriage might be preferentially preserved in certain minerals. We've seen that in albite, and it appears to be so in quartz, as opposed to something like a carbonate. One thing to note, I was just talking about how methane cycling can really deplete these carbon isotopes. That's what's thought to have occurred here at the Fortescue excursion 2.7 billion years ago, when you saw a large, maybe possibly evolutionarily advancement of methane cycling metabolisms. I think that's a pretty cool thing. So looking into the Archean, one thing I work on is microfossils. So we tie carriage and carbon isotopes to microfossils to try and better understand very early evolution of life. These are all of the known microfossil occurrences in the Archean record. So it's a few dozen. So anything you find nowadays is a huge contribution to this. So most of these things are relatively small, less than 50 microns, but there have been more recently found some of these larger coccoid things, which are exceptionally large for the Precambrian and particularly the Archean record, where they get up to 300 microns in diameter. What the heck are those things is a good question. So here's just another way of portraying that. This is just some images collected, some from Schaff et al. 2007, and some of these new extra large coccoids discovered by Sujitani et al. In 2010 and Javot et al. In 2010. 2010 was a good year. So mostly filaments, small coccoids, some of these kind of bacillus-shaped things, and really, they're so simple. The morphologies are so simple that you have a very hard time tying it back to a modern microorganism and saying, yeah, that's what it is. Oh, that filament? Oh, yeah, it's a sulfur oxidizing bacteria, no doubt about it. So we need to find other methods of finding evidence to explain basically the paleoecology of these fossils. And one way you can do that is with carbon isotopes. So some of my work at UC in Cincinnati, I was also working in the Cap Val-Creighton from South Africa, the 2.52 billion year old Upper Gamahan Formation, which is part of that Campbell-Wren supergroup. And it's basically the distal portion of that carbonate platform. And so what we found these pretty large things. These scale bars here are 50 microns. So they're relatively large, on an average 125 microns in diameter, all the way up to like 265. And so when we viewed them transverse to the bedding plane, you can see that they're actually preserved and somewhat show kind of almost a resistance to compaction between individual layers of sediment, which was a pretty interesting taphonomic feature. When you basically slice along one of these layers, you're looking at it from the top down, and you get a much better idea of how spherical this thing is. My advisor always likes to say it's like a poked beach ball. So it was it used to be this big, large sphere, but it's gotten all the pressure out of it, and it's flattened, and you can move it around, you can twist it, fold it, and those are the kind of things that we think are happening here. Also, when you're viewing them in these bedding planes, you can see some of these filamentous microfossils. So something we started to speculate about was whether we might be seeing two different communities, one a benthic chemosynthetic one, and one a planktonic photosynthetic one. But based on morphology, you can't say that alone. So what you need to do is you need to plug into carbon isotopes. And thankfully, nowadays, SIMS has become a very useful technique for doing this. So we can use Raman to measure the carriage on a micron scale of an individual microfossil, and then pair that with carbon isotope evidence of an individual microfossil. And this has been done pretty extensively over the last few years. Williford et al. In 2013 published this lovely paper. And so what you can see basically is they noted two microfossils with different morphologies, and they wanted to say, okay, do they have a similar carbon isotope signature? So when they measured them, they noticed that these ones are roughly negative 29, these ones are roughly negative 22. So this suggests that there was a slightly different carbon fixation pathway that existed within these things. And so that's what we're looking to find out. We did bulk carbon isotope measurements on these things, so we extracted the carriage, put it in a mass spec, and we got about negative 35. So if you remember that chart earlier, that's kind of at the tail end for photosynthesis. It's a very extreme depletion for purely photosynthetic, which are more typically around negative 25. So the question then is, do we have two populations, a photosynthetic one and a benthic chemosynthetic one? So we'll be going to University of Wisconsin-Madison to work with John Valley and do some SIMS analyses on these things. Wouldn't be right if I didn't come to Astrobiology Conference and didn't talk about Mars. So a lot of this research does have implications going forward, particularly for sample return, I think. But Curiosity has already detected some organic compounds, which is great because that wasn't even its primary mission. So it's just stumbling upon these things. And now we have Mars 2020, which is much more directed at searching for organics and signs of life. And sample return is something that I think a lot of us very much hope to be a part of. It'd be really, really neat to get them back and throw the kitchen sink at them here. And so I think that what we're trying to do now is use Raman in the deep UV, which is this Sherlock instrument, which will be on 2020. And we want to look at organics in things that are known biological organic matter. And if we can see what those look like in the deep UV on Earth, then if we see that on Mars with Sherlock, then we'll have a good idea of what samples we want to snag up and cache for later. And who knows what the Europeans are doing. So yeah, finding life in organics is difficult. There's other ways that you can produce organic matter that is carriage-like and depleted in carbon isotopes, right? So just those two things alone, you can't say biologically for sure. You really have to take a holistic approach. And that's going to take a lot more research. One thing I'd like to do in my PhD is look at these different forms of organic matter and try and see if there are some characteristic differences in them that we might be able to discern the biogenicity of any organic matter we detect on Mars, which would be awesome. So how do we determine abiotic versus biological synthesis of organics? That's the big question, I think, right now in terms of this. So with that, I'd like to acknowledge my advisor, my committee, my thesis committee, my funding sources, and absolutely the AbGradCon organizers. Great job, guys. Appreciate it.
Questions for Jeff?
If you're looking at your sedimentary samples from 2.5 billion years ago, how prevalent are these features in them? Do you have to look really hard, or do you slice it open and they're pretty abundant and they're always there?
So by features, I think you're talking about the microfossils?
Yeah, exactly.
Okay, so searching for microfossils is a very painstaking thing to do. It is. So sometimes you'll go through 300 thin sections and not see a thing. Sometimes you'll pop one in there and it's just filled. So in this case, they were pretty isolated. We probably went through 20 or 30 thin sections, no, maybe 20, and found maybe 100, 150 microfossils. So, and most of them aren't that well preserved. They don't look that good. So I put up the ones that look nice so we can all.
Do you know how that compares to like more recent millions of year old microfossils? Just trying to get an idea of abundance from back then compared to modern day.
Oh, in terms of abundance, well, I think you have a lot more life.
Well, yeah, that's why I wonder if it's
so you have
easy
more
if you just see
biomass
them
just all over
everywhere.
the Earth, so there's more likelihood that you're going to have microfossils preserved. But really, what it comes down to is the preservational processes. So microfossils in the Precambrian are really only preserved when you have early silica replacement, and you have this chert formation that basically it traps everything before the carbonate grains can grow large enough to break everything apart. So you really need early diagenetic silica replacement to preserve microfossils, which was much more common in the Precambrian when the oceans were supersaturated with silica. But now you have organisms in the oceans, in the waters, that are secreting silica, taking it out. So it's just not a prevalent process nowadays.
Okay, thank you.
Yeah.
Actually, I have a sample preparation question. I'm wondering, when you prep your samples for an isotopic analysis and ramen, can you utilize the same thin section, or can you talk a little bit about that in terms of the sim preparation in ramen?
Okay, ramen is a lot easier than Sims. That's for dang sure. I learned that the hard way. Ramen is non-destructive. So it's, you can zap it and it won't do anything to it. Unless you zapped it with a deep UV laser. That's some of the problems they're having with Sherlock, is that it can alter the sample. But in the visible wavelengths we were using, it doesn't alter the sample at all. So you can hit it with ramen, but once you hit it with the Sims, it's ablating it. So you're gonna lose some material there.
But you can use the same thin section.
You can use the same thin section, yeah.
Okay, let's thank Jeff one more time. And now we're moving into our poster session for the morning.